I'm going to present sort of our viewpoint on how the memory model should change, which has some similarities to what Miralee just presented and some differences. And I'll try and communicate our reasons for those differences. And on here, you can see I have this formally evaluated with TriCheck. So TriCheck is a tool in a long tool suite that we've been developing at Princeton for memory consistency model verification. So verifying microarchitectural implementations against their ISA level memory models. TriCheck is the latest tool in that line of work, and we've been using that to evaluate our proposed changes to the RISC-V memory model and how those, try and quantify how those affect RISC-V's ability to serve as a target for C++ programs. So just a little background, quick plug for the importance of an ISA memory model that's complete is IBM first introduced this notion in the 1960s as a way for them to essentially write one piece of software and then have that software run well on a variety of different hardware implementations at different price points for different customers. So the ISA memory model, and the ISA in general, has to be the definitive spec of what hardware looks like as seen by the software. So hardware has to implement the ISA in order to be considered a valid instance of that ISA, and then it's also the target for compiler translation. So if we look at, I tried to sort of draw this balance here, some strong ISA memory model like sequential consistency or TSO places more constraints on optimizations that microarchitects can take advantage of, but then requires relatively few ordering primitives like fences or barriers to be inserted by the compiler, so it makes that compilation part a little bit easier to reason about. On the other hand, we have very weak, more complex memory models, like you heard in the last talk, ARM and Power, that allow microarchitects to aggressively optimize their designs, but then require more explicit ordering in the form of the compiler inserting fences or barriers to uphold high-level language memory model requirements. So just a little bit of quick background on our work. So the first two tools in our line of memory model verification tool suites are this pipe check and CCI check. So these allow us to verify that a microarchitecture and its corresponding memory hierarchy are sufficiently implementing the ISA memory model. We then had this ARMOR work where we worked on more precisely defining memory models in a way that they can be sort of directly compared with one another for instance, maybe translation between memory models. Then we have this code check work where we looked at the subtleties that arise when, for example, ghost instructions that are executed on behalf of hardware page table walks interact with ISA instructions in the memory model. And then this most recent work, TriCheck, where we've tried to start looking at full stack memory consistency model verification. So taking the memory model as it's defined at the software level. So for example, the C11, C++11 memory model, and the promises that makes to the programmer regarding how concurrent code will run, then how that gets translated down to the ISA memory model, so the compiler mappings from high-level language ordering primitives down to the ISA, and then finally, how the microarchitectural implementations are implementing that ISA and how those high-level language programs are running, because ultimately, we need to be able to ensure that we're keeping the promises made to the programmer at the software level, we're upholding those when we're running on the microarchitecture in the end. So memory model bugs are observed in practice on modern hardware. So one example of this is the ARM read after read hazard. So this was a case where the ARM ISA spec was ambiguous regarding whether or not same address loads should be executed in order and as viewed by all other cores or threads in the system. So if you think about two loads to the same address, if you have two writes to the same address on another thread, reordering those two loads to the same address can make it appear as though two writes of the same address on another thread were reordered, which would violate coherence. So the C++ high-level language memory model requires that loads of the same address be executed in an order as viewed by everyone in the system. And so ARM issued this errata saying that compilers should be rewritten to insert fences in the appropriate locations to preserve these ordering. So this was first observed on the Cortex-A9 by this Oglov et al., but we have since observed it more recently ourselves on a Snapdragon 805, so Google Nexus 6, I believe. So these sort of bugs do exist in practice. So we just started by looking at the memory model as defined in the current ISA spec, which, as we understand, is still in flux, but we wanted to sort of characterize it as it is now and look at the ways we think we could modify it to sufficiently support high-level languages like C++. And I will also note that the modifications we propose are mostly compatible with current implementations, as these would affect more aggressively optimized designs. So what should we require from the hardware? So just a quick background on sequential consistency. So the first strictest memory model defined by Lamport, where an execution is the same as if these sequentially execution is one that meets each of these two criteria. So the first being that the memory operations of each thread are going to appear in the order they're written in the program. So you can see this by, hopefully you can tell the difference in color. The black instructions are executed in order in each of the threads, and so are the red instructions. And then the second requirement, which was often referred to as store atomicity, is essentially that all threads have to agree upon a single total order in which they're seeing accesses. So the first criteria essentially refers to how operations from a single thread are happening, and then the second requirement is dealing more from a global view of the memory system. What are other threads allowed to see? Are they allowed to see things that differ from each other or not? So, yeah, as I just mentioned, preserved. So there's sort of two categories of memory model relaxation broadly as it applies to an ISA. So one is preserved program order. So for sequential consistency, all program order is preserved program order, but for something maybe like TSO that wants to allow this write buffer optimization where they can forward read values from a write buffer, they allowed the reordering of writes and reads. So for various reasons, different memory models want to relax different aspects of program order. And then store atomicity, in which there are sort of three flavors. So one being this multiple copy atomic, which is all cores seeing a store simultaneously, essentially as if there's one monolithic memory and all threads are writing and reading from memory. And when a store is performed by a thread, everyone sees it simultaneously. And that's like sequential consistency. Then we have this read your own write early multiple copy atomic variant. So this is where something, for example, allowing for a private store buffer. So cores can read their own stores before other cores. So having a private store buffer. And then stores, when they are made visible to everyone else, are made visible simultaneously. And this is like the variant that we just saw in the previous talk for WMM. And then we have this non-multiple copy atomic variant, which is what RISC-V currently mentions in the manual. And this is the idea of having, you could think of it even like a shared store buffer, although you can implement this behavior without a shared cache of any sort. You can implement it with, for example, a forwarding directory protocol. And we've modeled that using our tools, and does maintain coherence, but does allow this intricate non-multiple copy atomicity of stores, which is that stores become visible to remote cores in a variety of orders. So the core performing a store may read the value first, and it's eventually made visible to other cores in the system. But when an outside core can read the value, it doesn't mean that all of the other cores in the system are able to read the value yet. And this is something that Power and ARM allow. This behavior actually hasn't been observed on ARM hardware, but is observable on Power hardware. So this is just a summary of some of our, what we believe would be good for RISC-V's preserved program order and store atomicity relaxations, and I'll explain our reasoning for some of these in a minute. Just wanted to highlight what the explicit differences are, at least in terms of preserved program order, and that is we want to require that reads of the same address maintain order so as to preserve C++ level requirements without having to force simpler implementations to unnecessarily insert fences to enforce that ordering. We also want to, I think, I made, let's see, I made a mistake in one of these arrows. So or one of these circles. So ignore the second circle, the middle circle. The larger circle on the right-hand side refers to ordering of dependencies, so read to write dependencies, and this is enough to also forbid that no thin air example that was talked about previously, which essentially happens when you're speculating the value of a write, and then sort of that allows the write maybe to appear out of thin air as viewed by other threads. And then we want this non-multiple copy atomic stores, and that's mostly what I'm going to focus on for the next couple of slides. And this is that case again where stores are allowed to essentially propagate to other cores in a variety of number of steps. So I'm going to just give a quick example of the effects of these non-multiple copy atomic stores, and then I'll give our reasoning for why we think that RISC-V should permit these to be implemented in RISC-V designs. So this is a 4-threaded program, and this non-SC outcome I have listed at the bottom is essentially this non-sequentially consistent outcome that can only happen if thread 2 and thread 3 read the writes on thread 0 and thread 1 in different orders. So if we had something like sequential consistency, it would require that all threads agree upon that store order. And in this example, the outcome at the bottom corresponds to a case where that is not true. So this is sort of analogous to what Murali mentioned in the previous talk about if cores were to share maybe a write-through cache. This is just easier for me to depict here, although a write-through cache is not the only way in which these stores, non-multiple copy atomic stores, can occur. So if thread 0 and thread 2 were to share a store buffer or write-through cache, and thread 1 and thread 3 were to share the same, so yeah, this is, once again, this outcome corresponds to the stores being seen in different orders by the last 2 threads. Then it is possible for, I don't know if this laser pointer works. It is possible for essentially thread 2 to read the store on thread 0 before it's gone out to the rest of the memory hierarchy, and the same for the first load on thread 3 can see the store on thread 1 before it goes out to the rest of the memory hierarchy, and that results in them seeing these stores in different orders. So why should we allow this non-multiple copy atomic store behavior if it's so confusing sometimes? We believe that, as we've seen today, RISC-V is intended to be used in a variety of SoC type environments. Could very well be interacting with GPUs, many accelerators that don't have memory models or have weak memory models. And if we want RISC-V to work seamlessly in a memory hierarchy that allows this lazy reordering of stores, we want RISC-V implementations to at least be aware that they could be subject to viewing that sort of weak store behavior. So while a RISC-V core itself doesn't have to implement non-multiple copy atomic stores itself, it could easily implement something stricter than what the ISA requires. But we believe in order for it to work seamlessly in a shared memory environment, RISC-V must be aware that stores could be observed in orders that differ from other cores. So if we allow this sort of non-multiple copy atomicity, what sort of special fences or barriers would we need to support C++? So this is that same example that we saw before. This is sort of an odd notation that I'm using. I'm meaning it to be sort of an acronym. So this PS stands for predecessor and successor, and the C stands for cumulative. So this is a fence ordering reads and writes to subsequent reads and writes, and its predecessor and successor cumulative, which I'll explain what that means. So whenever we have this notion of non-multiple copy atomic stores, we have to have a way to essentially enforce ordering of memory accesses on other threads with respect to the accesses on the fencing thread. So this fence, which I'm going to show the example just for the thread 2 fence because it's less cluttered that way. So the base case for this fence would be the predecessor set, so the things being ordered before the fence, will be all reads and writes on that thread itself. So in this case, it's the load of X into R0. The successor set base case will be all the reads and writes that follow the fence in program order. So in this case, again, that's this load of Y into R1. Then this fence is additionally going to order essentially writes that have propagated to that thread. So if this thread 2 has read, so if R0 is 1, which means it's seen the store on thread 0, then that 2 is going to become part of the predecessor set, so things that are being ordered before the fence. Additionally, in order to essentially restore a sequentially consistent outcome in this case, we need to ensure that everything that was in that predecessor set has made its way to another thread before the thread views the fence. So if thread 3 sees this fence, it must have first seen the read that happened before it in program order, and it also has to see what caused that read to read the value of 1. And this allows us to maintain causal relationships and sort of message passing type tests in the presence of these relaxed non-multiple copy atomic stores. So this is just a very brief summary of some of our suggestions at a very high level, and we have a sort of an archive paper for more details on some of our thoughts. But in the baseline model, one change is that we would like preserved program order to require same address read-to-read ordering. So to preserve coherence is required by the C++ high-level language memory model. We would also like to maintain order between dependent instructions. I think I heard somebody mention it earlier, but alpha is really the only sort of known instance where dependencies are relaxed, and we believe that dependency ordering should be enforced by default, which would be the case in most simple implementations anyways. So we don't think it makes sense to sort of pay the price of inserting extra fences to support dependencies. Then in the baseline, we think we should just have this strong predecessor, successor, cumulative style fences, like we saw in the previous slide, which for most designs maybe that are simple designs that are implementing the baseline ISA maybe aren't as aggressively optimized. This wouldn't be a very expensive fence on most of those implementations anyways. But then in the baseline plus atomics extension, we would like to add this additional predecessor cumulative fence, which essentially allows the ISA to take advantage of some performance features that C++ has provided at the language level. So C++ now in the C11 standard has this atomic type. So when a variable is declared with the atomic type, essentially it means that variable is volatile or can be accessed by multiple threads. And so those atomic variables, the programmer can then annotate with memory ordering primitives, like, for example, there's an acquire primitive, a release primitive, an SC acquire primitive, and an SC release primitive. And so these SC variants could be implemented, or must be implemented, with this strong predecessor and successor cumulative fence. But C++ supplies these relaxed acquire release operations so that hardware, for example, or power does this, can take advantage of a lighter weight fence for implementing those, so we don't need to use the same fence for both variants. And that's where this predecessor only cumulative fence comes in. So I'll go through a quick overview of the TriCheck framework for our full stack memory model verification and how we've applied it to our proposed changes for RISC-V. So essentially, we can start in the upper left-hand corner here. So we start with this suite of C++ litmus tests, and where a litmus test is essentially a small program, a few threads, and a couple to a few instructions per thread. And we run all of these tests on this C++ herd model. So what that is essentially actually, this is an incorrect citation. This should be Batty et al., Popple 16. And so what that is essentially a C++ simulator. So herd allows a designer to specify a formal axiomatic model of a memory model using this domain-specific language called CAT. So in this 2016 POPL paper, there is a C++ CAT model that is presented, and this CAT model essentially will allow you to pass in a small C++ program, and the model will then tell you what are the permitted or forbidden outcomes according to C++ for that program. And so we essentially, if you follow this left-hand side of the flowchart, we take this set of C++ tests, we run it on the C++ simulator, and we determine for each of these programs, say like one specific set we tested was about 1,700 programs. We say, what does C++ permit or forbid for each of those programs in terms of outcomes? Then we have this compiler mappings from C++ to RISC-V. So these are just not taking advantage of any sort of compiler optimizations, but just one-to-one mappings from C++ to RISC-V. And we get this should say small suite of RISC-V programs, not C++. And then we run that set of RISC-V programs on our basically RISC-V check model. So all of those check tool suites I mentioned earlier, we create various models of RISC-V. You can think of it as sort of a design exploration from very strict variants that are stricter than what the ISA manual requires to things that are really pushing the envelope. And then we see if the C++ outcomes match the ISA level outcomes in terms of kind of two main things we're looking for. So one, we're looking to see if there are outcomes forbidden by C++ that would be allowed under the current RISC-V specification. So that would signal sort of a fundamental bug that we would need to reevaluate. And then we're also looking maybe for instances where the C++ model allows an outcome that is forbidden given the current RISC-V memory model. And that may or may not correlate to performance, but it could be interesting in some cases to know that your ISA would be stricter than what the language requires. So yeah, just to reiterate, if the ISA does not allow outcomes prohibited by the ISA, if C++ does not, RISC-V does not, this is essentially what I just said. So the two cases we're looking for, this is the case where C++ is stricter, C++ is weaker than what the ISA implements, so maybe performance left on the table. This is the bug case that we need to look for when the ISA allows outcomes that are prohibited by C++. So just to go over a few results. So this is, we conducted essentially a preliminary analysis of the memory model as is. So the memory model that's currently out there in the manual. And then we subsequently applied various fixes of the sort of our proposed changes to the memory model, and then reevaluated to compare strictness versus bugs versus equivalence to the high-level language requirements. So just to explain this chart, along the bottom, this WR, RWR, et cetera, are just microarchitectural models that we implemented in our domain-specific language that express various ranges of weaknesses that are allowed by the current memory model. This WRC at the bottom is just a name for one of the small programs we tested. And in that program, we created 243 unique variants that would be possible given the current C++ high-level language memory order primitives. And then we ran all of those both through the C++ simulator, through our tool suite, and then compared the results. So you can see these last three variants right now. The RISC-V ISA model allows for the non-multiple copy atomic writes, but doesn't currently have the correct semantics for fences to restore those orderings. So these three instances where we see bugs are from the lack of fences, these cumulative fences to restore non-multiple copy atomic orders. And so in our variant, we add these non-multiple copy atomic stores that help us remove these bugs. Oh, and then I was just noting, so here we use that weaker predecessor only cumulative fence in these results, but we our proposal would be to have only the stricter variant included in the baseline design to keep it simpler that way. I have some more results at the end if we have time, but feel free to look at my slides online. Some ongoing work in conclusion. So right now we have formulated an English language diff of the current spec, but I'm working on constructing a formal model using that herd cat language that we use to describe the C++ model. So what that would do is essentially allow you to take any small program, input it into this RISC-V memory model simulator and determine what the output would allow for. And one nice thing about this is it, we decide to change one aspect to be different than what our proposal currently is. You could tweak the model in such a way to account for that change. And then we have just a couple notes. So memory model design choices are complicated. They involve reasoning about the subtle interplay of many diverse features. So it really is important not to define a memory model in light of one design, but to try and do this design space exploration of all the microarchitectures that could be conceived for a particular ISA, so that you make sure that you kind of cover for any fun things people might do in the future. And then our tool chain TriCheck is generalizable to any ISA, and uncovered and quantified some flaws or some characteristics of the RISC-V memory model, and also quantified some of our proposed solutions to fix them. And then feel free to check out our tool suite at this check.cs.princeton.edu. We have all of our tools on GitHub. And then we have a preprint of an ASPLOS paper where we're proposing this tool flow on archive for anyone to check out. And thank you.
Great, thank you. Steve's all set with a question. Go ahead.
Since you're proposing extensions, which I think is great, have you ever thought of having in memory full empty bits and other things that will, someone older than 50.
So you said full empty bit. Sorry, can you repeat the first part? Because
I said, since you're looking at extending the architecture, which
yeah.
is great. In the past, people have used something called full empty bits as a way of dealing with atomic operations and other things. I'm just wondering if that were to exist, how that would impact your memory model consistency models.
So one thing in terms of extensions, we're looking in particular at the current RISC-V memory model has the baseline memory model, and the baseline plus atomics extension has essentially its own memory model with the additional LRSC style operations and specialized read modify writes with acquire and release bits. So, or acquire and release bits. So we are essentially looking in our memory model analysis. We're looking at atomic memory operations, but you could easily in our framework modify like micro operations, or for example, we model like ghost instructions for hardware page table walks, things like that. This was a simpler analysis, but you could expand it to any of those.